Welcome to iLecture Online, and here's a very interesting example of how to use rotational motion. Let's read the problem. The pulsar at the center of the Crab Nebula, and you may say, whoa, what's a pulsar? Well, a pulsar is the remnant of a dying star that has gone through a supernova, and typically through very strong gravitational forces, they collapse into a very small, dense, very dense remnant, which we call a pulsar. And that pulsar inside that nebula rotates 33 times every second on its axis. Wow, so it's spinning really fast. The radius of a pulsar like that is about 10 kilometers, about 6 miles. So what force is required to keep an object on its surface? So let's draw a little picture of it. So here's a very fast spinning pulsar. Radius is about 10,000 meters, 10 kilometers. About 6 miles, and it's rotating in such a way that the angular velocity omega is equal to 33 revolutions per second, and of course we're going to have to convert that to radians per second. Imagine something that's spinning really fast. So in order to keep an object on its surface, you have to have centripetal forces, and the centripetal force in this case is going to be provided for by the enormous gravity on that pulsar. So if we draw this thing, so let's say that you try to stand on the pulsar, which I don't recommend because the gravitational forces are so strong that it would basically flatten into thin little pancakes, so you don't want to land on the pulsar, but let's say you could. Then of course you would require some forces to pull you in, so that would be the centripetal forces, and that is equal to mv squared over r. So those are the forces required to keep you on. Let's see here. To do that, of course, we know the radius. Let's say we know the mass of the object. We just assume that the mass of a typical person is maybe 80 kilograms, as an example. Then we need to find the velocity. So somehow we have to convert omega to velocity. All right, let's do that. So omega, first of all, we're going to convert from revolutions per second to radians per second. So radians and revolutions. And the one revolution is 2 pi radians. So that's how we convert omega from revolutions per second to radians per second. Now we also have to have the conversion from angular velocity to linear velocity along the surface of that star. So we know that the linear velocity v is equal to omega times r. So we then go ahead and grab this. We have velocity is equal to omega, which is 33 times 2 pi. That's radians per second. And we're going to now convert that to tangential velocity by multiplying times r, and the radius is 10,000 meters. So now we see that since radians is one of those non-units, we have now meters per second, which is the tangential velocity of an object on the surface. That's start. So let's go ahead and calculate that. So we have 33 times 2 times pi, and then times 10,000. And it looks like 2.07 million. So velocity is equal to 2.07 times 10 to the 6th meters per second. All right, so now we plug that in here. Remember, this is from rotational motion that we did back in the days that we talked about Newton's second law. The centripetal force equal to the mass times the tangential, or I should say radial acceleration, right? So this is m times a centripetal, not square, but ma. So this comes from Newton's second law in rotational motion. So we're now going to say that this is equal to m times v squared over r, which is equal to the mass. We took a typical person of 80 kilograms times the velocity squared. That would be 2.07 times 10 to the 6th meters per second. We square that, and we divide the whole thing by the radius, which was 10,000 meters. And that gives us kilograms meters per second squared, which is the units of newtons, or force. So let's do that. We square this amount, and then we multiply times 80, and then we divide it by 10,000. And that means to keep a person from spinning off a neutron star or a pulsar, that is equal to 3.44 times 10 to the 10th newtons. So that's about 34 billion newtons required to keep you from spinning off this fast spinning star. Now it turns out, luckily, I don't know, I don't think you ever should try to land on a neutron star. There's enough gravitational force to keep you on, even though you're traveling so fast that the centripetal force required to keep you on the planet is 34 billion newtons. All right, a quick recap of what we did. We were given a fast spinning object. We were given the angular velocity in revolutions per second, which we converted to radians per second. We then remembered from long ago that F equals ma, and the centripetal acceleration is v squared over r, so the centripetal force required to keep an object on a spinning object like that is mv squared over r. Since we found v by converting from angular velocity to linear velocity using that equation, we found the linear velocity, we plugged that in here, we squared it, and it gave us the centripetal force required to stay on the surface. Of course, if you compare that to the Earth is spinning much slower, doesn't require nearly as much force to keep you from spinning or flying off the Earth. A much, much smaller force is required. And again, Earth's gravity also keeps you on the Earth, so you don't have to worry about flying off due to the spinning motion of the Earth. All right, so a fun little example. Let's see if I can come up with something else as well.